main field of study is. Just maybe 10 seconds each so that I have a better idea how to gauge my lectures. You did yesterday, okay, sorry. Well, or maybe I can just do a poll. So how many cosmologists are there? How many people have seen the gravitational wave propagation already? Okay, so maybe today's lecture will not be new to most of you. Well, I suppose everybody has seen the Einstein equations of general relativity. Is there anybody who hasn't seen the Einstein equations of general relativity, gauge transformations, diffeomorphisms? Nobody. Okay, well, this should be okay. So today I will be talking about the equations regulating the propagation and generation of gravitational waves in general relativity. So the starting point will be the Einstein equations that we all know and love. So G mu nu equals 8 pi G T mu nu. So I will be setting C equals 1 for the most part of these lectures. So these are the equations for the generation of the gravitational field. They are the equivalent of the Poisson equations in the Newtonian theory. So what we want to do today is to consider a space-time which is a small perturbation of the Minkowski space-time. So I want to write my metric as the Minkowski metric plus a small perturbation h, with h mu nu much less than 1. So h has no dimensions, so it should be much less than 1. So it's a small perturbation. So if I invert, so this should be familiar to most of you. If I invert this metric, what I will get will be this with the opposite sign. So this is simply, you obtain this simply by inverting this metric. And the other, so what we want to do is now to insert these ansatz in the Einstein equations and linearize the Einstein equations. So because I assume that h is very small. The other piece of, the other ingredient that I will be needing today will be the concept of gauge transformations, which most of you, or all of you, will have seen already. So as you know, if you have an infinitesimal transformation of the kind, coordinate transformation of the kind x mu nu tilde, these being the new coordinates, plus a perturbation psi, where again psi is much less than 1, then this metric perturbation changes under gauge transformations in the following way. H mu nu minus this is the coordinate transformation. So this comes, as most of you will have seen already, by the transformation law for the metric. So G mu nu in the new coordinate x tilde will be simply given by G mu nu evaluated in x, function of x tilde. Sorry for my handwriting. Sorry, I should call this prime. Right. So if you take this, the tensor transformation law for the metric and insert this infinitesimal coordinate change and expand at linear order, you will find that the metric perturbation in the new coordinates, the tilde coordinates, is given by the old metric perturbation plus these two derivatives, which are actually the Lie derivative of the background metric. So most of you will have seen this. This is almost the definition of Lie derivative in general relativity. So this is all background material. So what I want to do, as I said, is to insert these ansatz into the field equations and linearize, and then use this gauge transformation to show that there are just 2 degrees of freedom for the gravitational field when you expand over flat space. So how do you do it? Well, first of all, you need to calculate the left-hand side of this of the Einstein equations, and it's more convenient to do it in what we call sometimes the Lorenz gauge, because the expressions are simpler. So let me introduce this object, which is what we call the trace-reversed metric perturbation, for reasons that will be obvious in a while. So this is, by definition, h mu nu minus 1/2 the trace times eta mu nu, where h is defined as the trace, indeed. So again, indices of the first-order perturbations are raised and lowered using the background metric. So this is, if you want, equivalent to eta mu nu h mu nu. So this is called the trace-reversed metric perturbation, because if you calculate the trace of this object, the trace of h bar equals the trace of h minus 2 the trace of h, because the trace, of course, of the metric is 4. So you get minus h. So this is an object which has the opposite trace as the original metric perturbation that we introduced. So far I've done nothing but defining this object. What I want to do now is to use this gauge freedom that I have to impose this condition, which is called sometimes the Lorenz gauge condition, which is inspired also by electromagnetism, if you want. This is called Lorenz gauge. Note that there is no T here. This is not the same Lorenz as the Lorenz of the Lorenz group. It's a different Lorenz. So this gauge condition is familiar, probably. You probably have seen it in electromagnetism already. So I want to impose this Lorenz gauge condition. So why do I want to do that? Because the equations for the left-hand side of the Einstein equations are much simpler if I use this gauge condition. And in particular, this implies that the Ricci tensor R mu nu is simply minus 1/2 of box h mu nu, where box is the D'Alembertian operator. So by definition is the D'Alembertian operator of the background metric, in this case the Minkowski metric nu. So if you want, if I use Cartesian coordinates, this is simply given by, depending what signature I assume, minus dt squared plus nabla squared, where nabla is the Laplacian. And you can see already that in this gauge, essentially the left-hand side of the Einstein equations will give you some sort of wave equation, which we now specify better. So I'll move here. So now, well, you know that the Einstein equations are simply given. So for the moment, actually, let me consider the vacuum case. So I will not consider, how do you spell vacuum? No, probably like this. So vacuum, so I set T mu nu equals 0. So I'm only concerned with the propagation of gravitational waves at this stage. So what I want to solve is G mu nu, or actually right, is G mu nu equals 0. Now G mu nu is simply, as you remember, R mu nu minus 1/2 R G mu nu in general equals, actually, sorry, I don't want to I'll focus on the vacuum case later, so sorry for this. Let me, for the moment, G mu nu equals 8 pi G T mu nu. I want to write G mu nu as, of course, by definition, R mu nu minus 1/2 R G mu nu, and this must be equal to 8 pi G T mu nu. Now what I can do is to take the trace of the Einstein equations. So what do I get? I get R, you probably have seen this many times, minus 1/2 R, the trace of the metric. The trace of the metric is 4, so I get minus 2 R equals 8 pi g t, t being the trace of the stress energy tensor. So this becomes, of course, minus r equals minus 8 pi g. So you can rewrite the Einstein equations as 8 pi g t mu nu minus 1/2 t g mu nu. And you can see the appearance here. So I've just rewritten the Einstein equations by replacing the trace, and you can see here the trace reversed. So if I can define this as the trace reversed stress energy tensor, T bar T mu nu, because as you can see, it's the same, I mean, it satisfies the same definition as this. So T mu nu is by definition T bar mu, the trace reversed stress energy tensor. So now, I want to replace my linear expansion in these equations. So I wrote here that r mu nu equals minus 1/2 the box of h mu nu. So what do I get? I get minus 1/2 the box of h mu nu. This gives me 8 pi g, the trace reversed stress energy tensor. So at this point, I've linearized my field equations. And now what you can do is to note that if you define this, this trace reversed operator, when applied twice, gives you the original perturbation. So if I apply the trace reversed operator twice, the trace reversed operator is given by this over bar. This gives me h mu nu. And similarly, if I apply the trace operator twice to T mu nu, this gives me T mu nu itself. So what I can do now, therefore, is to apply the trace reversed operator to this equation. And what do I get? I get minus 1/2 box, the trace reversed the trace reversed metric perturbation, minus 1/2 h bar mu nu. And then here I have 8 pi g t with 2 bars mu nu. Oh, there is a g here, sorry. And because of this identity, what this is simply 8 pi g t mu nu. So you've seen why I introduced this trace reversed operator, because this is what naturally appears on the right-hand side of the field equations. So this equation is the equation for the propagation of gravitational waves. And in fact, I will rewrite it somewhere because I will be needing it in the next probably half an hour. So if I just multiply by minus 2, I get a box of h bar mu nu equals minus 16 pi g t mu nu. Okay. This is the equation, and this is valid, again, in the Lorenz gauge, defined by this condition. So this is the equation for the propagation, because this is a wave equation, of the metric perturbations over flat space. So remember, this h mu nu is defined, is related to the original metric perturbation by that relation. So we get a nice wave equation. And in particular, you see that in this box operator, what appears is the speed of light. So I've set c equals 1 in this calculation. But if I had not set c equals 1, here I get 1 over c squared, which would tell me that these perturbations follow essentially the wavefronts of these perturbations follow null geodesics. So they propagate with the speed of light, follow null geodesics of the background Minkowski metric. Is there any question at this stage? How many of you have seen this stuff already? So most of you. So should be easy. This was this might have been useless, but let me say something that I'm not sure, maybe you have seen already. So this gauge transformation, or this gauge condition, doesn't actually specify the gauge in an unambiguous way. Why? We have seen that the metric perturbation, well, I rewrite it here. Maybe I should use a different sign for, so I'll write the gauge transformation for the metric perturbation in this way, by indicating the new metric perturbation with a prime, because if I use a tilde as I did above, it will be similar to a bar due to my bad handwriting. So let me rewrite the gauge transformation for the metric, which is, as I said, nothing but the Lie derivative in this way. Minus. So now, if I use the definition of, suppose now I want to see how H bar, the trace reversed metric perturbation, transforms under gauge transformations. First of all, because H bar is defined, I mean, it's rather trivial, so I should just remember that H bar mu nu is H mu nu minus 1/2 H eta mu nu. And I use this gauge transformation in the definition of H bar. What this gives, if you do the algebra, is that H bar prime mu nu equals, I will give you the result, H bar mu nu minus So what I've done here is simply to take the definition of H bar, the trace reversed metric perturbation, and see how this transforms under this gauge transformation. So what do I need to do to get this equation? I just need to take the trace of the gauge transformation and replace it in the definition of H bar, essentially. And what you find is this gauge transformation for H bar. So suppose now I have, let me write somewhere else, maybe here, yeah, maybe I write here. So suppose I have a gauge such that the Lorenz gauge condition is satisfied. And perform now a further gauge transformation x mu equals x mu plus So suppose now I perform another gauge transformation. So I have a gauge, a Lorenz gauge, and suppose now I perform that gauge transformation. So I perform a further coordinate change, and I want to see how this gauge condition changes. So to check that, I just need to take, if you want, the derivative contracted with the index mu of this gauge transformation here. So let me do that. I just take the derivative of h bar prime mu nu. What do I get? I now take the same derivative of the right-hand side of that equation, minus, what is it? I get derivative with respect to mu of psi nu, plus, sorry, eta, oh, sorry, there is another term, minus d mu psi okay, sorry, I got the indices wrong. So d mu psi mu plus eta mu d mu d and now these two terms should cancel. So you see now I can invert, of course, these being partial derivatives. I can rewrite this term as the derivative with respect to nu of d mu psi mu. And of course, this index, I can raise it with the metric, so this becomes d nu. So these two terms, this becomes d nu, d alpha, psi alpha, and therefore these two terms cancel out. And what I get here is simply the divergence of h bar mu nu minus the box of psi. So this tells you that any gauge transformation whose generator psi satisfies a homogeneous wave equation, let me write it, also satisfies the Lorenz gauge. So this shows you that the Lorenz gauge doesn't specify, the Lorenz gauge condition doesn't specify all of the gauge freedom. So you still have residual gauge freedom when you impose the Lorenz gauge condition. So the Lorenz gauge condition is preserved by gauge transformations with generator satisfying a homogeneous wave equation. So I still have the freedom to make a gauge transformation of this kind without changing the form of the perturbed Einstein equations that I obtained before. So at this point, I want to put myself in vacuum. So vacuum, that is T mu nu equals 0. So my perturbed Einstein equations will become simply a homogeneous wave equation of this kind. So box of h bar mu nu equals 0. And I still have this residual gauge freedom to play with. Okay. So these are, and I remind you, this box is nothing but the flat box operator. So this is a very easy equation to solve, or these are two easy equations to solve. So this implies that the solution is h mu nu equals some constant matrix, or as we call it, polarization tensor, A mu nu times EI K alpha X alpha, where K alpha, let me write it explicitly, eta mu nu, K nu equals 0. So this is simply the usual plane wave solution of a wave equation. The only complication is that here, instead, because you have a tensor here, you need a polarization tensor in front of it. And similarly, this equation gives you a particular solution is given by a plane wave. So let me call it, what did I call it here? Yeah, call it B, without much imagination. B mu nu, EI K alpha X alpha. So these are the two, this is the solution, and this is the gauge transformation that I can still perform. So now, what I want to do at this stage is to play with these coefficients B, which are 4 coefficients. I have 4 gauge transformations, to reduce the number of independent components that this polarization tensor has. So this polarization tensor has in principle 10 independent components, because h mu nu is symmetric. So there are 4 indices here. There are 2 indices, each of which can take 4 values. So in principle, A mu nu has in principle 10 degrees of freedom. And I want to see if I can reduce these degrees of freedom by 4 minus 4 using the 4 free coefficients B mu. Right. Actually, sorry, I did the counting wrong, because I recall you that actually we also had to satisfy the Lorenz gauge condition, which is, so A has in principle 10 degrees of freedom, minus 4 Lorenz conditions, minus 4 B mu. So in the end, I expect that I will be able to reduce A mu nu, the polarization tensor, to just 2 degrees of freedom. Again, in principle, it has 10 degrees of freedom. I impose the Lorenz gauge condition, which amounts to 4 independent conditions, because the index nu, takes 4 values. But even if I impose this Lorenz gauge condition, I also have residual gauge freedom in the form of these undetermined coefficients, B mu nu. So I expect that in the end I will be able to reduce the degrees of freedom of the metric perturbation to just 2 degrees of freedom, which would be the 2 polarizations of gravitational waves. How am I doing with time? I think I'll write here. So let me show this explicitly. So we've already done the counting, but Let me do it explicitly for you. So first of all, do I still have the gauge transformation? Yes, there. So first of all, I want to see if I can use one of these coefficients b to set the trace of the metric perturbation to 0. So to this purpose, let me just, well, I rewrite it there. So let me take my good old gauge transformation that I wrote up there. H mu nu prime equals H mu nu minus d mu and let me take the trace of this equation. So if I take the trace, I get that the trace transforms in the following way. So the trace in the new coordinate system, in the new gauge, equals the trace in the old system minus 2 minus twice the divergence of the generator. And let me now use this form for the generator because I want to use a gauge transformation that preserves the Lorenz gauge condition. So if I do that, I get minus 2I k mu b mu k alpha x alpha. So I've just replaced this form for psi here. I've taken derivatives. So the only dependence on x is in the exponential, so I get a wave vector here. So, and as you can see, by choosing B in a suitable way, I can choose, let me write it here, I can choose k mu times b mu such that h prime equals 0. So I've used now part of my residual gauge freedom to set the trace of the metric perturbation to 0. But I've only used one component. So I've only used one scalar, b contracted with k mu nu, to this purpose. I still have 3 degrees of freedom here, because this b mu nu has 4 degrees of freedom. It's a full-fledged vector. So I want to now prove, let me write it here, I will show that, well, you can do it as an exercise, that I can set also h prime h bar ti to 0. So I want to use the remaining 3 degrees of freedom for B to set the cross terms, the cross components. With I, this I here is of course a spatial index, and T is the time index, of course. I want to set the T time space components of h bar to 0 using this 3 residual degrees of freedom. How do I do it? Well, again, I take my, I can do it very quickly. Let me, so I can just take this gauge transformation and see how, well, in fact, I think I deleted it. I need a gauge transformation for h bar, which I deleted. You should probably have in your notes. So I remind you that h bar prime mu nu equals h bar mu nu minus d mu plus theta mu nu T alpha psi alpha. This was the gauge transformation for h bar that we derived before. And now what I want to do is to specialize this to the Ti component. So without, let me just erase here. So I write Ti here. I can write Ti here. So this becomes a T, this becomes an I, this becomes an I, this becomes a T, and this becomes an IT. Now, of course, in Cartesian coordinates, the Minkowski metric has no space-time cross terms, so it has no IT component, so this term goes to 0. And I find that HTI bar transforms, therefore, in the following way. And now if I insert the explicit form for B mu nu, this becomes HTI bar minus I kt bi ei k alpha x alpha minus k I bt e. So I've now just replaced, again, my residual gauge freedom in the gauge transformation. And you can see that I can choose, for instance, the spatial components of the B vector to set HTI bar to 0. So I can choose BI such that H bar Ti prime equals 0. So now I've shown that I can choose, for instance, the time component of this vector B to set the trace of the metric perturbation to 0. And I can choose the spatial components of this vector B to set the cross terms to 0. So I'm almost done. So I've taken care of these 4 degrees of freedom that are in the B, in this B vector. There are still conditions on this polarization tensor that come from the Lorenz condition. So, but those are quite easy to obtain or to understand. Let me. So remember, the Lorenz gauge condition is simply given by this. And I want to replace, in this condition, I want to replace the explicit plane wave solution that I derived before. So what do I get? I get the derivative of A mu nu, let me do it explicitly, A mu nu, what do they call it, AI k alpha x alpha. So now if I take the derivative, the only dependence on x in the argument of the exponential in the phase. So I get I k mu, A mu nu, ei k alpha x alpha, and this needs to be 0. This is the Lorenz gauge condition. And so I get, in particular, that k mu nu, k mu A nu equals 0. This is my Lorenz gauge condition. And also, because of the 4 residual gauge transformation that I had, I also have that the trace of H needs to be 0, and H bar Ti equals 0. So in particular, if you combine, so now let me consider a plane wave that propagates, for instance, in the z direction, plane wave along z axis. So if I have a plane wave propagated along the z-axis, so this k mu, this vector k mu, is given, I write it in components. The equal sign is, well, let me write this. It will be 1, 0, 0, 1. So this is the t component, and this is the z component. So in particular, k mu a nu nu gives me that equals 0 implies that a t nu must be equal to a z nu, right? Because if I lower the indices to get this k mu with index down, this one becomes a -1. So when I do this contraction, I find that a t nu equals a z nu. This is a nu, sorry, for any nu, right? Then, if I also remember that h bar t I equals 0, this implies, if I use my expression for h bar, this implies that a ti equals 0. Right? This is the same thing. And then if a ti equals 0, from this relation, if I set nu to I here, I also get that a z I equals 0. I just use this relation in here. And then, again, from this relation, I mean, this is trivial if you do it yourself, but I'll do it here. If I set nu equals t, I get that a tt equals a zt, but then a zt, because of this relation, is 0. So if you go through this, this is trivial algebra if you want, but it allows us to, if you put all these conditions together, we get something interesting. If you put all these conditions together, you get, let me write this as a matrix. So we got that ATT equals 0. Then we got that a tz equals 0, so these two terms are 0. Then I got that a zi equals 0, so z, yes, this equals 0. And then in principle, I should have also a ti equals 0. So I have all these 0. And then remember that, so I have in principle just these 4 entries that can be different than 0. But then remember that the trace of the metric perturbation is 0. So these two need to be opposite. So this, let me call H plus and minus H plus. And then these two components can be non-zero, and let me call them Hcross. So in the end of the game, so we used the Lorenz gauge condition and the additional freedom on the that is left by the Lorenz gauge condition to reduce the independent number of degrees of freedom of my metric perturbation to just 2 components. And this is what we sometimes call the H plus, the plus and cross polarization of gravitational waves. So this is, if you want, a wave along the z-axis. So, and as you can see, it's a transverse wave. So if the wave is propagating along the z-axis, the only components that are not zero are in the plane orthogonal to the propagation of the wave. So this is why, in general, we say that the gravitational field has only two independent degrees of freedom in vacuum and over flat space. What time is it? So one comment that I would like to make is that to obtain this result, I've used gauge freedom on the one hand, but also the field equations. So here, in deriving this result, I use this plane wave solution for the gravitational wave, which comes from the Einstein equations. So this wave equation comes from the Einstein equations. So if I were to modify the Einstein equations and go to a more general theory than general relativity, this result wouldn't be true anymore. So it wouldn't be true that the gravitational field only has two independent degrees of freedom. There would be extra polarizations for gravitational waves. So for instance, the trace in theories of gravity that extend GR, the trace of the metric perturbation doesn't need to be zero and could be a propagating degree of freedom itself. And in fact, this is how one of the ways in which we try to test theories of gravity that extend general relativity, by looking for additional polarizations of the metric perturbation. So how many of you have seen this already? Most of you have seen this already. Okay, not everybody. So now I'm saying something that hopefully, or I think you usually don't find it in textbooks. So I want to generalize this construction to curved space. So far I've only linearized over flat space, over the Minkowski metric. So I want to see how things change if I go to a more general background. I think I don't need this part anymore, so let me. And I want to show you that, in fact, things are, I will not go through all the details because the equations are more complicated, but I will try to show you that things are different. So in curved space, so of course, what I mean by curved space is that G mu nu is different than the Minkowski metric. I can still introduce the same trace reversed metric perturbation as I did before. So I can define h bar mu nu equals h mu nu minus 1/2 h g mu nu. I still have the freedom to do that. This is just the definition. And I can also impose a covariant Lorenz gauge condition. So I can require that the covariant derivative of this object, h bar, contracted with the index mu equals 0. This is, again, Lorenz gauge condition. So if I do so, and I take my Einstein equations and crank the numbers and expand them at linear order, what I find is this equation, h bar alpha beta. Then I have couplings between h and Riemann. I'm not sure if I want to write all the terms. Plus other terms, which I will not write explicitly, that depend on G mu nu, R mu nu, etc., which I don't care about for reasons because I want to put myself in vacuum, equals minus 16 pi T mu nu. Sorry, T alpha beta. So here you have an equation which looks similar to the one we derived in vacuum. So you have box of h bar. This box is now the flat space box, is the curved space box. This is by definition. I also have a coupling between Riemann and h bar, plus I have other terms that I will not write that depend on the Einstein tensor and Ricci tensor, which in particular, if I put myself in vacuum, these terms will disappear. So I consider a metric which is not flat, but which is vacuum. So these terms I can neglect. So I get an innocuous looking equation. So I get box h bar plus Riemann contracted with h mu nu equals some source, the stress energy tensor. And I can try to see how many independent degrees of freedom there are in h bar. So I can try to do the same trick as I did before. I can try to use the residual gauge freedom of the Lorenz gauge to perhaps reduce the number of degrees of freedom of my metric perturbation. So I will not go through all the details. What you can do is that, and you probably know already, that in curved space, the form of the gauge transformation as linear order is simply given by h mu nu prime equals h mu nu minus 2 the symmetric part of the covariant derivative of the generator of the gauge transformation. This is nothing but the expression of the Lie derivative of the metric. You could write this as minus the Lie derivative along psi of the metric g mu nu. As a matter of fact, it's essentially the definition of the Lie derivative. So we can now try to see how the Lorenz gauge condition transforms if I change the gauge. And by taking the derivative of this expression, you get nabla mu h bar prime mu nu equals mu. So I've taken the derivative of this term, and now I want to take the covariant derivative of this term. Okay, sorry. But as a matter of fact, I need first to go from this gauge transformation to the gauge transformation for h bar. So I need to use so if you do this, you'll find that the covariant derivative of h bar transforms in the following way. So I'm not going to derive it, but you can do it easily. The same calculation we did before in flat space. So we find that any gauge transformation, let me write it here, any gauge transformation such that box of the generator equals 0 conserves the covariant Lorenz gauge condition. So we still have some residual gauge freedom. But unfortunately, so the situation looks similar to what we had before. Unfortunately now, however, this box operator is not the flat box operator anymore. It's the box operator over a more generic metric on a more generic background. So I can't go through the same procedure that I went through before, in which I solved those equations using a plane wave ansatz. I can't do that anymore because this box operator is now more complicated. So I can only find you can't in general find plane wave solutions if the box operator is generic. There are no plane wave solutions in Schwarzschild, for instance, or in Kerr. So I can't go through the same procedure as before. Still, I can show that using this residual gauge transformation, I can set at least the trace of the metric perturbation to 0, even in more generic backgrounds than flat space. So I'll not be able to go through all the derivation because it's actually quite involved. But the idea, I can try to give you the idea. So suppose I want to, right here. And maybe we can break for 5 minutes, maybe not. So suppose now I want to set H prime to 0. I want to use in the residual gauge transformation. So first thing I need to understand is how H prime, the trace, transforms under gauge transformation. This is H prime equals H minus 2, the divergence of the generator. So I would need to set, I would need to choose, of course, the divergence of the generator equals to H halves. Okay, so this is what I would need to do. But remember that your generator must satisfy this homogeneous wave equation if I want to preserve the Lorenz gauge condition. So in general, if I have a wave equation, the only thing I'm allowed to do is to specify the initial data for that wave equation. So here, if I want to preserve the Lorenz gauge condition, I can only choose the initial data for the generator at t equals 0. So I only have the freedom, since I need to satisfy this equation, I only have the freedom to choose, if you want, psi mu at t equals 0 as function of the spatial coordinates, and if you want the time derivative of psi mu at t equals 0 as function of d. So I only had the freedom to choose psi and psi dot on the initial hypersurface, on the initial foliation of my wave equation. So it's not obvious that I can choose the divergence of psi over the whole space-time to be H halves, because this needs to be verified for all t and xi's, whereas I only have the freedom to specify psi at t equals 0. However, well, a miracle happens, because if you can show by using this equation, so let me call this equation star. So star plus box x mu equals 0. So this is the equation for my residual gauge freedom, and this is the Einstein equation. These two together imply that the box, and the calculation to show this is quite long because it involves commuting covariant derivatives and so on and so forth. You can show that the box of this equation, where again the box is the curved space-time box, let me call it box G. So the Einstein equations and the residual gauge transformation imply this yet another wave equation, this wave equation here. And so what I can choose, so this shows you that if I choose if I choose equals 0 at t equals 0 and the derivative of at t equals 0, then equals 0 everywhere at all t. So in general, if I have a wave equation, and if I choose the function, the degree of freedom that satisfies the wave equation to be 0 and have 0 derivative at the initial time, then that degree of freedom is 0 at all times. So if I now choose, so this combination satisfies the wave equation. So if I choose the initial data for this function to be 0 and 0 time derivative at t equals 0, then it follows that that quantity needs to be 0 at all times. And this quantity being 0 at all times means that I can choose, if you go back to this equation, it means I can choose h prime to be 0 at all time. H prime equals 0 on the whole manifold. So it's not trivial, but as you can see, it follows from the combination of it follows from the Einstein equations themselves. So in curved space, therefore, I can choose the trace of my metric perturbation to be 0, but it turns out I can do nothing more. So I cannot reduce the degrees of freedom of the gravitational field to just 2 degrees of freedom, as I was able to do in flat space, if I'm in curved space. And even in curved space, I can set the trace of the metric perturbation to 0 only because I have the Einstein equations. If I didn't have the Einstein equations, I wouldn't be able to set the trace to 0, and in general effect, yes, please.
So we start from the star equation.
Yeah.
And then we contract to get a vector equation.
Yeah.
We contract it again, and then we get a scalar equation.
Yeah. If you want the derivation, I can give it to you later, because I've done it, but then it would take me an hour to go through it. Yeah, so the idea is that, well, if you want, what you need to do is I would actually start from this equation. I would actually expand this equation, commute derivatives commute this box with this covariant operator until I can get, so I'll get a bunch of Riemann tensors, but I will also get box psi mu equals 0. So then I can set that to 0. And then I have a box applied to H here, for which I can use the trace of that. So I would actually go the other way around. I would start from this, but I can give you the derivation if you're curious. I mean, I did it some time ago, and it involves just commuting covariant derivatives with Riemann. It's not, there's nothing profound about it. Okay, so I'm afraid I don't have time to stop as I wanted, but in the last half an hour, I will try to tell you more about what are actually the degrees of freedom of the gravitational field in curved space. So far, I've only showed you that things are not as simple as in flat space. I want you, yeah, so let me say a few more things about the degrees of freedom of the gravitational field in general, in the presence of matter that curves the background space. So so in particular, I will go through so how many of you have seen the derivation of the equations for the cosmological perturbations? For instance, for the scalar, vector, and tensor degrees of freedom in cosmology. Yeah, so this will also be covered this afternoon. So what I will go a bit quickly, both because I don't have time and because you will see these things in afternoon. But I think it's interesting to also see yet another way of studying the degrees of freedom of the gravitational field. So I want to consider a space-time with matter. And this matter appears also only at first order in perturbation theory. Let me be more specific about it. So I want to consider a metric of this kind. Again, a perturbation over Minkowski space. And the stress energy tensor that is 0, well, of course, plus, so let me place a small parameter here. This epsilon is a small parameter. So the stress energy tensor is 0 at background order, but at first order in this epsilon, it has a perturbation, which I will call delta T mu nu. This is very similar to what you will, in a sense, to what you will see this afternoon. So I want to decompose now this metric perturbation according to the components of this metric perturbation according to their, there's a question? Sure. Sorry. You might also come closer, there is space. G mu nu equals 8 mu nu epsilon h mu nu. This epsilon is a bookkeeping parameter, so epsilon is order 1, and plus there are orders epsilon squared. And T mu nu, I call it starts at order epsilon. So I now want to decompose both the components of the stress energy tensor and the metric perturbation according to their transformation properties under spatial diffeomorphisms, spatial rotations, if you want. So in particular, for instance, let me say call HTT. I will call it, for reasons that will become clear later, 2 phi. So this is a scalar under spatial diffeomorphisms, because spatial, if I just change my spatial coordinates, and I keep time unchanged, HTT will not change, right? Then I want to decompose HTI in the following fashion. This is just the definition of this stage, beta I plus gradient of a vector gamma. So HTI is, of course, a vector under spatial rotations and spatial diffeomorphisms. So any vector, as you know from electromagnetism, can be decomposed into the gradient of a scalar, which I will call gamma, and a curl, or if you want, as it is sometimes called, a solenoidal vector. So this beta must satisfy this solenoidal or zero divergence condition. So this means that beta is actually a curl. This is a generic decomposition of any vector. In fact, you can prove it yourself. So suppose you can try to prove that this decomposition is unique. Suppose I give you a generic vector field, and you can try and obtain beta and gamma as a function of the components of that vector. And the way you do it is to take the divergence of this equation. If you take the divergence, this term cancels out. Here you get the Laplacian of gamma. Under suitable boundary conditions, you can invert the Laplacian and get gamma. And once you get gamma, you get beta. I don't know if it is clear. Maybe you'll see it more if it is not, come to see me during the coffee break, and if you're interested. But this is just the same decomposition that you do in electromagnetism. So So it's any vector is a curl plus a scalar. And then you can do a similar decomposition for Hij, which is of course a tensor under spatial diffeomorphisms. And this, I write it as, maybe I should write it somewhere else. Not have space, I'll write it down here. Hij, the Hij dt, and I will say what dt means, plus 1/3 H delta Ij. I'm trying to use as big fonts as possible. So this is the most generic decomposition under, well, there is a subtlety about the boundary conditions, which we'll not be concerned with today, but in general, if you have a 3x3 matrix or tensor in a rank 2 tensor in over a flat background, you can decompose it in a trace. This is nothing but the trace, so this H is a scalar. You can also write, if you have a scalar lambda, you can write a term of this kind, a traceless. You can promote the scalar to a tensor by taking two derivatives, and because you've already singled out the trace, you want to take the traceless part of this double derivative of lambda. So this is another way in which you can write a rank 2 tensor from a scalar. This epsilon is a transverse vector or solenoidal vector, so it satisfies this. So if you have a curl, you can make it a tensor by taking derivatives and taking the symmetric part. And this HDT Ij satisfies both the transverse conditions, so the contracting one of the indices with the derivative, you get 0, and also it needs to have 0 trace, HDT I equals 0. And again, you can prove that this decomposition is unique. To prove it, what you need to do is you need to solve this equation. Suppose I give you Hij, and you want to explicitly find the form of H, lambda, epsilon, and HDT. What do? You first take two derivatives of Hij, contracting the indices. Most of these terms will go away, save H and lambda. You can then take the trace of Hij, and again, all the terms will go to 0 except H, so this will determine H. And then you can take one derivative of this, contracting the index, so the derivative with respect to I of Hij. This will give you epsilon, and then all that will be left will be HDT. So you can try to do it at home, or maybe you will see it this afternoon. But this is the typical decomposition that you perform in cosmology when you study the CMB. And I want to show you how gravitational waves arise in this picture. I can't go through all the details, which you will in any case see this afternoon. You can perform a similar decomposition for T mu nu, this delta T mu nu. Let me, maybe this I can write. So again, T, capital T, 0, 0, or TT. So the time component of the stress energy tensor, let me call it for obvious reasons rho. It's a scalar under spatial rotations. Ti equals, again, a curl, the gradient of a scalar first, plus, let me call it plus a solenoidal vector or a curl that satisfies this boundary condition. and Tij, again, let me call it P delta Ij. So the trace of the stress energy tensor is simply the pressure, therefore I call it P, plus, again, I have a scalar mode, di dj minus 1/3 delta ij nabla squared, and let me call this scalar mode sigma. Then I have a vector mode, sigma j plus, how did I call it, sigma ij. So where now these sigmas satisfy the boundary condition, the following boundary condition. So the vector is a curl, so the vector is solenoidal, and this tensor sigma ij is transverse and traceless. So this is exactly, there is nothing new here. This is just definitions at this stage. And I've done the same decomposition as with the metric. So this is very, you will see this is in the afternoon. It's the basis for understanding the dynamics of perturbations of CMB. And now, so far, this decomposition is completely generic. So I want to use what you will see this afternoon referred to as the I think he calls it the Newtonian gauge. I prefer, sometimes it's called the Poisson gauge. So I want to use gauge freedom to set some of these components to 0. So in particular, gauge freedom are I have 4 degrees of freedom. I have 4 coordinates, so I have 4 degrees of freedom. So I can set 4 of these objects to 0. So first, let me set this to 0. So let me set gamma to 0. So this is just one scalar, so it's 1 degree of freedom. Then I want to set this solenoidal vector, or curl, to 0. And how many conditions does that use? It uses 2 conditions, because epsilon satisfies this solenoidal condition, so it only has 2 degrees of freedom. So far I've only used 3 degrees of freedom out of my 4 gauge transformations. And finally, I will also set this lambda to 0. So this is called the Poisson gauge. So if you're cosmologists, you will know, or maybe you already know, that this Poisson gauge choice gives you exactly, is related to what is called the Bardeen formalism for gauge invariant quantities. So it's equivalent to using gauge invariant quantities as defined a la Bardeen. Conceptually, it's nothing but using my gauge freedom to set 4 numbers to 0. So 1 number here, gamma here, 1 number, lambda here, a scalar, so therefore another degree of freedom, and epsilon I set it to 0, and I can do that because it only has 2 degrees of freedom, because it doesn't have 3 independent, although it has 3 components, one of the components is related to the other 2 by this solenoidal condition. So let me see. Okay, so now what I want to do is, in fact, I said I wouldn't explain the relation to the Bardeen gauge invariant quantities, but I actually need to do that. Although so I will not again go through all the details, which you will probably see this afternoon, or I can give you my notes, or can give you references. Let me now, so I've now used the Poisson gauge, and let me now introduce these quantities. Capital phi minus small phi plus, I'm not sure if it is worth writing down, but it would be easier to just show them on the screen, but let me quickly write them down. Theta, by definition, is 1/3 h minus double squared lambda, and let me call it sigma I equals beta I minus 1/2 epsilon I. So this is somewhat, if you want, a mystery at this stage, but these are the, it turns out that if I take these combinations of the, these are the Bardeen, so these are gauge invariant quantities, and if you consider my gauge choice, this lambda equals 0, this gamma equals 0, lambda equals 0, lambda equals 0, and epsilon equals 0. So these are the Bardeen gauge invariant So by making this gauge choice, my phi coincides with the Bardeen gauge invariant potential big phi, my h corresponds to theta, and this beta corresponds to sigma. So this is one way of understanding why I make this gauge choice. But why am I telling you all this? Because I want to show you the field equations for these quantities, for phi, for beta, for h, and for HTTIJ. Or equivalently, I want to show you the gauge equations for these Bardeen gauge invariant quantities. So if you just replace in the Einstein equations and again crank the numbers, linearize them, etc., you find the following equation. So you find that this theta, which for me is simply h, satisfies an elliptic equation. So it doesn't have a propagating. So I think there is a g here. Here I'll be setting g to 1 here. Sorry about this. So g will be 1 from now on. Nabla squared of big phi equals 4 pi rho plus 3p minus 3 s dot. Remember, s is the components of the stress energy tensor. Nabla squared of sigma equals minus 16 pi si. And finally, an equation that by now will look familiar, HTTIJ equals minus 16 pi sigma ij, where the sigma ij is now the transverse traceless part. Where is it? The transverse traceless part of the stress energy tensor. So now you see why I was saying before that when you have when you're not in vacuum and in flat space, there are degrees of freedom that you cannot get rid of. So I showed it before in the case of the so the equation for perturbations over curved space, but you see it again. There is no way in which I can gauge away these two scalars, theta and phi, or as a matter of fact, this sigma, if I have matter. If I have no matter, the sources for all these three elliptic equations is 0. So I can conclude that phi, theta, and sigma are 0. But if I have matter, even if I'm outside, suppose I'm outside a rotating body. So rho will be outside, it will be 0 outside this rotating body, but still I will not be able to set theta to 0 outside the body, because the solution, even if I have a compact source, theta will go as the mass of the body divided by r outside. So even if I'm in vacuum, if I have matter in some portion of the space-time, I will never be able to set theta or phi or sigma exactly to 0. And you can understand it easily because this phi is essentially the generalization. Is it phi? Yeah. So it's phi is HDT, so it's the relativistic generalization of the Newtonian potential. So I will never, so if you have if you have a star, even if there is no matter outside the star, you'll never be able to set the Newtonian potential to 0 outside the star, because the Newtonian potential is, satisfies this elliptic equation, so the phi or theta decay as m over r, but they never go to 0. So this shows you already, this shows you again that there are more than 2 degrees of freedom describing the gravitational field in vacuum if you have matter. The thing is that these gravitational degrees of freedom, extra gravitational degrees of freedom, are non-propagating. So they satisfy elliptic equations, unlike the transverse traceless perturbations, which satisfy this box equation. Of course, this box here is now some perturbing over a flat space. This is the flat box. So there are still 2 propagating degrees of freedom, but there are other degrees of freedom that satisfy elliptic equations. So what are these degrees of freedom? Well, the first one you've seen already. So HTT I've mentioned already. This is the Newtonian potential. So this phi generalizes the Newtonian potential. So at lowest order, so if I were to reinsert c in this expansion, I would have a c squared here, a c squared here. So when velocities are small compared to the speed of light, this potential phi satisfies the usual Poisson equation. When I expand, if speeds are, if you want, are not negligible compared to the speed of light, these terms are not negligible, so I have to take them into account, and this is what we call a post-Newtonian expansion. Similarly, this theta is h, so it appears in the space-space component of the metric, is a potential that, well, seems similar to the Newtonian potential, but its physical meaning is actually different. So for those of you who have seen the post-Newtonian expansion, this theta appears in the dynamics of matter at 1 p.n. order, and for the dynamics of light at leading post-Newtonian order. So it regulates, if you want, the light bending of stars, sorry, the light bending of around the sun. This is the way in which general relativity was first tested, through the light bending, the bending of stellar light by the sun during eclipses. And this term is exactly what regulates that bending. Whereas this psi is also a 1 p.n. effect, meaning that it's negligible when velocities are small compared to the speed of light, but it becomes important when velocities are non-negligible with respect to the speed of light, and this is called the lens steering potential, or frame dragging potential. Essentially, this is a vector effect. It's so this vector is what is it? It's a curve. So it has a direction. It carries a direction. And this is why if you have a rotating black hole, for instance, and you observer try to move in the opposite direction as the rotating black hole, you will feel a drag. You will eventually co-rotate with. You will tend to co-rotate with the rotating black hole. So this also affects motion of objects around the Earth. In fact, there were experiments such as Gravity Probe B that tried to measure the frame dragging due to the rotation of the Earth, as predicted by general relativity, and this frame dragging is exactly described by this vector potential. So how many of you have seen the post-Newtonian expansion? Very few. So maybe I will spend the last, since I don't have much time to start deriving the quadruple formula, maybe I will try to explain to you why those terms appear at higher p.n. order. Let me see, I have some notes. This is useful in general. I might have to change slightly the notation, however. Yeah. Yeah, so this is, I'll try to keep the same notation, although yeah, so in order to, of course, the post-Newtonian expansion is an expansion of the field equations in 1 over the speed of light. So unfortunately, I'll have to, by definition pretty much, to reinstate all the c, the speed of lights, in my calculation. So let me consider, well, coordinates x naught equals c times t, and Cartesian coordinates xi equals x, y, z. Okay, so I'll put my c in the, so I want my coordinates have the dimensions of lengths. And then let me write g0, 0, minus 1, minus 2, phi. So this 2 phi is the same as there. And let me put a c squared here. And let me say that g0i, so I called it there beta, so I'll still call it beta, beta I over c to the third. Let me explain why I'll put a c to the third. And gij, what did I call it there? So I have a delta ij from the background. It'll be a pain to... I'm sorry, I think I'll slightly change the notation. You'll forgive me for that. I will explain now. So ij plus htt ij or c squared. So what I've done here is to simply copy this ansatz. I put some c's here, and it will become clear in a why. I put the c's in the following way. The only thing I've done, I've called this h. I've done just a rescaling, and I called it psi. So, but it is still the trace. So as you can see, it's still the trace of gij, just because in my notes somehow I changed notation. So why do I put the c's in the way in which I put them? Because if I were to I'm free to do it. This is just an ansatz. If I replace into the field equations, what you get is that you get equations similar to those, or exactly such as those. You get that you get the phi satisfies, for instance, 4 pi rho 3p over c squared. This is the same equation that I wrote there, plus other terms. So you find that phi from this equation equals the Newtonian potential. This is the lowest order in 1 over c. This is the Newtonian potential, plus a term that I will call phi 1pn over c squared. So if I don't put a c squared in here, I will not get, at leading order in 1 over c, I will not get the Poisson equation. So if I make a mistake here, if I were to put over c to the 4 here, I wouldn't be able to get a consistent solution. So I will be forced to put a c squared here. And similarly here, if I were to put bi over c here, I would find that beta I would be 0 from the field equation. So I have to put a c to the 3 here. And this 3 to the, if I put a c to the 3, I will get an equation such as the one that I got before. Again. I will not write all the times, sorry. Pi rho vi, sorry, getting smaller and smaller. 4 pi rho Bi, where Bi, so what I'm doing here is now to introduce the velocity of matter. So it's not completely consistent, but I hope I will give you at least the idea. So this Bi, so this is exactly the same equation as the one I wrote here, but I wrote this Si, which was one of the components of the stress energy tensor, which I've now deleted, or maybe not, yeah, I've deleted it. I've written it explicitly in terms of the velocity of matter. So this beta I, if I write it as 1 over c to the 3, is sourced by rho Vi. There is no 1 over c here. So this gives me that beta I starts with a term of order 1 over c, 0. So if you want, if I write these ansatz, both phi and beta, when I insert the ansatz in the field equations at leading order, they do not depend on C. So if you want, I singled out the dependence on C in the ansatz. So why am I doing all this? I hopefully now it will become clear. Oh, I didn't write the. No, sorry, I didn't. Yeah, so I wrote it here, and similarly here, Hij. Well, from the field equations, you'll find that Hij dt, if written in this way, oh, actually, yes, so I should put a c to the 4 here. Hij dt, we start order c to 0. Okay, so if you solve the field equations again, you'll find that G00 will have a term of 1 over c squared, given by the Newtonian potential, plus terms of higher order than 1 over c. G0I will start with a term of order 1 over c to the 3. Gij will have a term that starts as 1 over c to the 2, and then later a term that starts as 1 over c to the 4. So this comes again from just the field equations, solving the field equations, expanding the field equations in 1 over c, and noting at what order deviations from flats, at what order in 1 over c deviations from flat metric start appearing. And the last 5 minutes, I will explain why we call those 1pn potentials or Newtonian potentials, which we also use tomorrow to some extent. Okay, so how many of you have seen the action for a point particle in GR, in your GR studies? Okay, good portion. So, so the action for a point particle in general relativity is simply given by m, mass of the particle, c squared, integral of d tau. Okay, this is what you vary when you do the first. This might be one of the ways in which you first saw the geodesic equation. You can vary this equation with respect to the trajectory of your particle gamma, and you get the geodesic equation. So what I want to do here is do something different. I want to use this action to derive the Lagrangian of a particle moving in a metric satisfying these ansatz. So how do I do it? Well, first of all, I remember that by definition, the action is the integral of the Lagrangian over time. This is from classical mechanics. So I want to re-express this action in terms of coordinate time to be able to read off the Lagrangian, minus m c squared, and then I want to change variable. So I write this by dt, d tau by dt. Tau is the proper time, times dt. And then what I want to do, so let me erase this to avoid confusion. And then we'll call it a day, minus m c squared integral. Now I want to express the line element or the proper time in terms of the metric, g alpha beta x dot, where the dot is now a derivative. Dot is by definition a derivative with respect to coordinate time. So alpha x dot beta over c dt. So I've taken care to keep all the c's in this calculation, although it's tedious. So these two go away. What do I do? I copy this, and now what I want to do is to replace these ansatz in the metric. So this ansatz, which again comes from solving the field equations. So I'm afraid I have to copy here 1 plus 2 phi over c squared. Then I have an x. So of course here I have x naught dot. This is c. Okay. So I have a c squared minus 2, and then I call that beta I c to the 3. So this is the g0i term, and then I have a c from x naught, and then I have an x dot I from there, minus gij x dot I x dot j. And then I have a square root somewhere here. So I've done nothing but replacing the ansatz for the metric here and keeping track of all the c's, which is tedious, but I've done it at home, so I shouldn't have made any mistakes. And then, as a matter of fact, yeah, so maybe I'll do it here. Well, I can simply call this x dot I call them v, velocities, vi. So this becomes vi vj. And then let me replace this gij. Sorry, to avoid typing everything, writing everything again, this becomes minus 1 minus 2 psi over c squared. I'm just replacing there, times b squared, minus, I call that, what did I call it? Hij tt over c to the 4, or c to the 4, vi vj. Okay. So hopefully you're seeing what I'm doing. I'm just replacing and keeping track of all the CIs. And then, and this gives me, and of course there is a dt here. So this is my Lagrangian. So now to make, since I'm expanding 1 over c, I can Taylor expand that square root, and you'll get something more clear, hopefully, which would be the end result for today. So again, S equals the integral of the Lagrangian over time, so I can extract my Lagrangian, and I can Taylor expand the square root, so I remember. So the square root of 1 over x is 1 plus 1/2 of x plus minus x squared divided by 8 or something, I think. So I do this Taylor expansion on the square root, and I get that my Lagrangian for a particle in a post-Newtonian expanded metric is given by minus m c squared, okay, fine, plus m v squared over 2. This comes from here, v squared over 2. This is the kinetic energy, minus m. And then I want to use this expansion. So I wrote that phi, at lowest order is given by the Newtonian potential plus corrections. So here I get minus m phi n. Plus here there will be a bunch of other terms appearing at order 1 over c squared. And these terms will be, for instance, let's see if I can write some of them. Well, I will not write all of them, but yeah, let me see, for instance, minus 1/2 phi n squared over c squared. Sorry, it's squared. Yeah, c squared, if I've done the calculation correctly, plus phi 1 pn over c squared minus, what did I call it, beta, let me use a vector notation, dot v over c squared, and there will be plus terms of order h, t, t, I, j over c to the 4. There will be terms that appear at order 1 over c to the 4 due to h, I, j. So you've seen now why I call those potentials post-Newtonian potentials, because at lowest order in 1 over c, well, at lowest order I get this term here, which is just a constant, so I can discard it. So it's a constant, I don't care. It doesn't affect the Lagrange equations because the Lagrange equations depend on derivatives of the Lagrangian. Here I have the kinetic energy of classical mechanics or Newtonian mechanics, the Newtonian potential, and here I have corrections that appear at 1 over c squared. That means in order 1 over c squared means is what we call 1 pn, 1 post-Newtonian. 1 post-Newtonian order is 1 over c squared. And I get terms that depend on htt that appear at order 1 over c to the 4. So this is what we call 2pn. And this is the last thing I will be saying today. Gravitational waves appear first at 2pn, and this is what we call, however, a conservative component, a conservative effect. 2pn, conservative effect of gravitational waves. Why is it conservative? Well, you can see it from the time reversal symmetry. So whenever there is a c, for dimension reasons, there needs to be a v. So this actually, v over c to the 4 is actually v to the 4 over c to the 4. So this term is time reversal symmetric, so it's a conservative term. Gravitational waves also appear at order 1 over c to the fifth power, which is instead a dissipative effect. So gravitational waves, as we will see tomorrow, take energy away from systems. In general, they carry energy in angular momentum. And so if you have a binary system of black holes or neutron stars, gravitational wave will carry energy away from the system. And this causes what we call a back reaction on the motion of the system, and it's necessarily a dissipative effect because you carry energy away. And this corresponds to what we call a 2.5 pn term. This is what we call 2.5 pn effect, and it's a dissipative effect. And it's, in fact, the back reaction of the energy that you lose through gravitational waves. So this is much higher order than what we're considering here. We're stuck to 1 pn, but if you expand the equations further, you will see that there is an effect at 2 pn, conservative effect, and 2.5 pn, which is a dissipative effect. And just because I've mentioned light bending, so in this calculation, I've shown you that these potentials, if you want, H, beta, or as I call them, psi and beta, appear at 1 pn order. But this is simply because I've assumed I started from the action for a point particle, for a massive particle. If I had started from the Lagrangian of a photon, or if you want a massless particle, the counting would have been different. So in particular, you can see it from here. So if I would have set V to C, so if I had set V to C, if I set V to C in this Lagrangian, yeah, I didn't write the term. There is an extra term that I wanted to write. Sorry. Well, the counting would have been different, and you would have seen that this potential psi would have entered at the same order as the Newtonian potential. I didn't do it properly here, but if you want to see this post-Newtonian approximation in more detail, which I was not able to do here due to time, you can look at, there is a nice book by Clifford Will, Theory. Well, it's done in many books, as a matter of fact, but I find this very well done and very concise. Theory and then experiment in gravitation. So I think it's chapter 5 or 6. Chapters 5 and 6. So he goes through exactly the same derivation. He starts from the Lagrangian for a massive particle and shows that you get first order the Newtonian Lagrangian plus post-Newtonian corrections, and he does the same for a photon, for light bending. So tomorrow, so I've talked a lot today about the Newtonian potential, the post-Newtonian potential, beta and psi. Tomorrow we'll look in more detail at the gravitational waves, in particular how they are generated. So we'll derive the quadruple formula, and we'll see that the gravitational waves carry energy and angular momentum. So we'll talk about the stress energy tensor. This is all for today.